Hello, in this video we're gonna mess around with ECS architecture. In the first part of this video we're gonna talk a little bit about what ECS architecture actually is and why we might want to use it. In the second part of this video we're gonna create a convenience wrappers for an ECS library that we're gonna use, and in the third part of this video we're gonna make a simple application that utilizes ECS architecture and the wrappers that we will have made in part 2. So let's move on to part 1. Well, first we need to have the understanding of what an ECS actually is, right? Well, actually the name kind of boils down the architecture pretty well. It's an entity, component, system, but it's an architecture. So it's not an entity component system, it's an entity component system architecture. So the word system in here corresponds to a part of an architecture. It's not entity component system, it's entity component system architecture. So each word has its purpose, functional purpose. Let's go through each word. So first, the component. Component is just data. Component has no behavior. I know that certain implementations of ECS do allow components, or people who use ECS sometimes do have behavior in components, and it's not that they're doing something wrong. So, but by ECS architecture, component is simply a data. It has no behavior. It's not a class. Components are not objects. They're just blobs of data. They have no behavior. Entity is a way to associate components. So entity is not a collection or a container. It can be viewed as a container of components, but it's not really. It's just a way to associate components. And system is just kind of a function, right, that performs operations on entities. And since entity is a way to associate components, it performs operations on related components. Now, for example, here we've got a bunch of components, a position component, one position component, then two mesh components, an audio component which has a growl audio track. We've got a cube mesh, a pyramid mesh, and so basically we have this and this. So here are two entities, so entity 1 and entity 2. So that's what I meant when I said entities are just a way to associate components. So here we associate those components, and they make up an entity. They make up a cube that is at this position, and it can growl, a growling cube. And this is a pyramid in those coordinates. And the reason why it's important to say that entities are a way to associate components and not just containers for components, because actually ECS architecture lets us store, for example, we could have an array of position components, and each position component belongs to different entities, but they're all stored together. So and it's like it's a performance thing, optimization thing, but yeah. And a system, for example, mesh render system, renders each entity that has position in mesh components. So the mesh rendering system is gonna check if, for example, entity 3, we don't know what that is, but let's say entity 3 is just an ambient sound. It's placed somewhere, it has a position component and an audio component. The mesh render system is not gonna take it because it has position component, but it doesn't have a mesh component. However, mesh render system is gonna look at entity 1, which has mesh component and position component, and it's gonna render a mesh at a position in a scene, and then it's gonna take an entity 2 component and it also gonna take it and render it. These entities can be however different as long as they have a position and a mesh component. For this rendering, for a mesh render system, it doesn't matter if entity 2 has an audio component or doesn't have it, and that kind of flexibility is one of the main features of ECS architecture. Okay, let's move on. The next question is, why do we want to use ECS? Why can't we just use class hierarchies? So let's look at an example. So here we have a game object, and then there are two classes that extend game object. One is audio class, which basically will be kind of like an ambient noise. So we place a game object which is audio, and it's gonna play in the forest, and it's gonna play the forest ambient sounds. And we have another class visible, so they're gonna be renderable. And then we extend visible with solid, a solid object, and then we extend solid object with wall, and then we could have another objects such as, I don't know, ground and stuff like that. And then we extend alive, so a game object that is visible, solid, and alive. And then we have two types of those visible, solid, alive game objects, which is a player and non-player character, which is gonna be powered by AI. It's gonna have an AI, artificial intelligence, some kind of behavior, but player, we're gonna control player with our gamepad or what have you. And okay, then we have an ogre, and ogre is obviously an NPC. Fine, but then we have a ghost, and a ghost in our game is not solid. So, and we wanna add this ghost, but if we add it here, it's not solid, so it doesn't really make sense for ghost to extend this thing. And then we could create a, for example, non-solid alive NPC. And so how do we go about fixing that? Well, let's try to change our class hierarchy, which, if we are doing that not as we are planning, but as we're actually writing out code, can be a big deal, right? Okay, so we have an audio that extends an audio game object, a visible game object, then we have a solid game object, a solid visible game object, an NPC visible game object, and wall is obviously a solid visible game object. And then ghost is gonna be a visible non-player character game object, but then where do we place in that hierarchy player, alive, and ogre? We could create a alive solid or solid NPC. So as you can see, it's difficult to design a class hierarchy that actually makes sense. You have to know, before actually implementing that class hierarchy, you have to know all the entities that are gonna be there to kind of plan it well, and it can be done, and it has been done. And class hierarchies may do for smaller games. And actually the reason why I even started using ECS is because I at first I was making a game, just a simple game, but still I was so confused how to create that hierarchy. I was constantly changing things. I had duplicate code in different classes. It was a mess, and that's why I started using ECS. So let's actually see how we could solve our problem with ECS architecture. Here we have a wall entity which is visible, has a sprite component, which is just data, right? A position component, obviously, the position in the world or in this on the screen, and a collider component. So that means that it's solid, right? So it's visible and it's solid wall entity. Now player entity is visible, it's solid, but unlike and non-player characters, we can actually control it with our keyboard and mouse or with the gamepad. So it has a controls component, whatever we might define it as, or something like that. And it can have a bunch of other components, and if we need a wall to emit some kind of to play some kind of audio, we can just add an audio component to it. Same as player, we can add components that are specific to this player, so it's much more flexible. And a ghost entity now, it is visible and it's not solid, so it doesn't have collider component, but it has script component AI. So it's a non-player character which is powered by a script and AI. And ogre might have sprite component, position component, collider component, and a script component. So it's flexible that way. That's why we might want to use ECS. So now that we have a basic understanding of what ECS architecture is and why we might want to use it in our applications, let's actually try it out in practice. We're gonna use Entt, which is a library, an ECS library. It's extremely fast, and it has a good documentation, which is actually even more important in terms of if you're starting out with a library, because I've used a bunch of libraries and one of them had effectively, like, practically no documentation, and it was really frustrating. So yeah, we're gonna use Entt, but we're gonna create convenience functions and wrappers, so they're for our convenience. So let's implement them. Well, I guess it's called entity, but I'm gonna call it this library Entt, just because not to confuse it with the word, the actual word entity. So we're gonna use a single include right here. So we're just gonna copy this file, this header HPP file, into our project, and it's gonna, and that's it. That's the whole process of actually including the library. Here is single include. You may want to use like release, because release is kind of a stable version, and here in the source code there's gonna be this single include folder, and to download it we just open it and press download, or kind of just save as. So now let's set up a project. So I'm gonna just create an empty project. Yes, let's create src. So we copy the single include Entt.hpp. So here it is, including project, and let's look up a simple example code, sample code. Yeah, we need to use C++ 17 standard. So in project properties we change C++ language standard. If you're using Visual Studio like me, we need to use C++ 17. Okay, so it compiles, so we've included the library. Now let's actually create convenience wrappers. So first we're gonna create scene. So I called it scene, but we could also call it world, or I don't know, like container for entities. Basically scene or world or whatever is just a container of entities, and that container can represent a scene or a game world, a game level. So let me make the code bigger. Okay, class scene. So actually the scene or the world in Entt is registry. It's called registry, and it's just a container for entities, and we're just creating a wrapper for this. So we're gonna have a forward declaration of entity. So the scene is gonna have create entity method, which is gonna create an entity in that scene, and we're gonna pass it a std string tag, because by our implementation every entity is gonna have a tag, which is kind of like an identifier of type of entity. I mean, however we choose to use the tag. And in entity class we're gonna have Entt entity is just an identifier to associate a bunch of components, and we're gonna have a pointer to the scene, because we're gonna implement these constructors here. Now, before implementing this function, we need to create a bunch more convenience function to add components, remove components, check if an entity already has a component. Let's implement those. So here they are. Basically we just wrap these functions. Add component, it's in place in entity. We could have a kind of debugging code. For example, we could check if an entity has a component. If an entity already has this component, we could print that hey, or log somewhere that entity already this component is, it already has that component. I'm just not gonna do that, but we could add it later on. So T here is like the component, the type of component that we're gonna add, and then we just in place, and here args are arguments for that component. So for example, if we had a position component, right, this we would use this function like that. So some entity e dot add component position, and then 125 and 40. So this here is the type, and these are arguments. So there can be multiple arguments, obviously, and we use std forward to it's a way to catch some bugs that we might have had if you didn't put it here. It keeps the it has to do with references, like it keeps them kind of valid, so it propagates them. Get component just gets the component, and remove component removes component, and has component checks if the component, if entity already has a component. And you see here we provide entity handle. So this class, this wrapper class, is just to have more kind of object oriented look to the code. And now we can actually implement the create entity function. This is how it's gonna look. We create oh, by the way, in order to use this registry field of a scene, we have to say that entity is a friend class of a scene, so entity has an access to private fields of scene class, so it has access to registry to use it here. That's really important. It's not gonna work otherwise. And so yeah, here we basically registry.create creates an entity and returns it. So it returns this data of that type. So we pass it in the constructor here, entity handle, and then we pass the pointer to the scene, and we return the entity object. And also, since we provide here a string and we want our entities to have a tag component, we're just gonna create components.h pragma ones, and here we're gonna place all our components. and the component that all the entities are gonna have is that component. It's just gonna have a tag, and we're gonna entity add component. Also we probably should. Let's do it here. I guess components.h tag component. We're gonna pass tag in here, and yeah, that's pretty much it. Now let's get rid of all that. Let's debug this now. So scene has a registry of size 0 at the beginning, just as we expect. Now we've created, no, we haven't created yet. Now let's create a ground entity. So now the registry has size of 1, and the ground entity has a handle 0, and the scene and the pointer to the scene. Now let's create a player entity, size, no, entities here, size 2, and the player entity handle is 1. So here you go, we've created a wrapper for our library. So let's create a simple application. We're gonna build a physics simulation, just because it's quite simple to do. I mean, with the game we have to do a bunch of extra stuff, like setting up the window and stuff like that. So I chose to make a physics simulation, which is we're just gonna use simply an ECS, and that's it. So it's gonna be a simulation of objects falling. They're pulled by gravity. The objects are gonna have an acceleration, a downward acceleration caused by gravity, and they're gonna have velocity, vertical velocity, and the altitude is gonna change. So let's do that. So let's create components for that. I'm not gonna have a mass of an object component, because in our simulation it doesn't matter what mass an object, a body, a fallen body has, because of inertia, x acceleration and y acceleration. So we're gonna have a scene. So let's create a function, create object. Now let's create an object at 500. I mean at 0, 500 probably, and let's see, and it's gonna have no 0 velocity, and then we're gonna create another object that's gonna be at 250. It's gonna have an upward velocity of 50, And now I'm gonna create two systems. The first system is print system, which is gonna print all the information about the position and velocity and acceleration of every object. And I'm gonna create a system, the move system, which is gonna update the values, the position and velocity, because with time velocity is gonna change due to acceleration, and position is gonna change due to velocity. And remember, systems are simply like just functions. While get, I don't know, char, get char, and so yeah, I've decided to move the systems into the scene. So scene is gonna have an update method, which we're gonna call each time we press enter. And because the simulation is gonna run too fast otherwise, so I have these two new systems, these two systems in the scene and a void update. I'm gonna show you the systems in a second. First, let's print system. So on update, we just call the system, and here so in the print system, this is one of the ways to kind of go through the view. So the view it takes all the entities that have certain components. So here we say basically, okay, we want from the scene, we want entities in the scene that have position component, a velocity component, and acceleration component. And for each of those entities, we want to print the information about each entity. So that's what each does. And it's a for loop which has references to the entity, actual entity handle, and then this is a reference to the position component, to velocity component, and to acceleration component, so that we can access them here. Pos.x, pos.y. So we're gonna print all the information, and in the move system we also take entities that have those components, and we set the acceleration. Maybe this shouldn't be like that. We set acceleration to minus 9.9, so downward 9.8 meters per second, or meters per second squared. And then we change the velocity based on the acceleration, and we change the position based on the velocity. And yeah, so on update we simply call these systems to perform their job. And we have two objects now, and yeah, so basically when we press enter, 1 second passes in the simulation. Hopefully this works. Okay, nothing happens. Why doesn't anything happen? Print F entity position. No, let's actually check this out. So let's go in here, we get the view. Oh, and we just exit, get the view, and we also just exit. Why does that happen? Oh, because I forgot to add acceleration component here, which is be 0.0 and 0.0 as well. And now here we can get rid of it. Hopefully this will work. So press, we go in. Okay, so yeah, so we do get now it seems to be working. Let's check this out once again. So I press enter, 1 second passes, nothing is changed, so it's the 0, not 1 second passes, but this is the, let's get a bit better by doing another n, maybe a bunch of those. So we've got two objects, so these are their position, velocity and acceleration in the moment of time 0. So as you can see, the position of the first object is 250 meters above the ground, and the velocity, it goes 50 meters per second in the upward direction, and the second object is 500 meters above the ground and it has no velocity, none of that. So 1 second passes. Now the acceleration is minus 9.8, so we let go, or so now the objects are free falling, so the acceleration is minus 9.8. Because, for example, this second object, we were holding it in a hand, so the acceleration was 0 because we were holding it and not letting gravity pull on it. The net force was 0, right? But now we let go, and the acceleration is minus 9.8. So the first object, it was flying 50 meters per second in the upward direction, so it is going still upward, but the speed is decreasing. And the second object, we just let it go, so it goes straight down with the velocity minus 9.8. Another second passes. Now the first object moves with even slower speed, but still upwards, and the object that we just let go, that had no initial velocity, is accelerating and going down. And here, as you can see, going down, Now the velocity of the first object, so it stopped and it now goes down, and the second object still goes down as expected, and so here we go. I'm gonna press Ctrl C to exit. Oh, okay. Yeah, that's it. As you can see, we've got a physics simulation that we can use to test different relationships between velocity and acceleration in the gravity. I mean, it's a very simple physics simulation. We achieved that by using ECS, and the point of it is just to show you how to use the ECS, is to show you how to create, make systems, right, and how to use them. But for more information, you should go here. And here, for example, there are different ways to create systems, right? There is a documentation in here, a wiki, I think. Yeah, I'm actually also want to show you how to actually get the component. So we get, for example, we want to get a position component that we've just added. We can do that like so: get component, position component, and position component reference, like that. Let's get this. Now position is 0,500. It's for this object. I just wanted to show that we should use reference here to get components. Yeah. Okay, there you have it. We have went through a bit of a theory on ECS. We've implemented convenience wrappers for the library of our choice, which is Entt, and we've made a simple application that utilizes ECS architecture. So I'm gonna put a link in the description to Entt library on GitHub, and I'm probably also gonna create a GitHub repository to store this code that we've wrote in this video, so that if you wanna check out the code, you can do so also by following a link in the description to the GitHub repository. So thank you for watching. Bye.